last class, we learned about energy in general and its relationship to work. Today, we're going to learn the mathematical definitions of the three most important or most common energy types. So these are gravitational potential energy, which we're going to call GPE, elastic potential energy, or EPE, and kinetic energy, or KE. So I'm going to start with GPE here. So this is gravitational potential energy. Or in other words, GPE. So the way that the equation for gravitational potential energy was discovered or made is also with work. So if you guys remember, the equation for work is force times distance. Force times distance. So someone thought, okay, so if I grab a book and I lift it up 1 meter, then how much force did I have to do to lift that book? So the force that we're talking about when we lift things, so if we have to lift an object up here, the force that we have to do is exactly the same as the force that is fighting against us, right? To lift the object. So the force that is fighting against us is actually gravity, which is m times g, right? So the force that we're going to have to make to lift the book at a constant speed is exactly the same force. So our lifting force will also be m times g. So when we lift that object, that book, that ball, whatever it is, through a distance x or a distance h, because this is going to be the height through which we move the object, then we can calculate the work using the force that we had to make and the distance that we lifted it through. So basically what we're going to get is that the work is equal to, so the force is going to be m times g, and the distance is going to be that height that we lifted it in total, how much height we lifted it, so times that h. And that actually became the equation for gravitational potential energy, because the work that you do to lift the object is exactly the same as the amount of gravitational potential energy that the object will acquire when it's up there. So that's why it was important to learn last class that work is that transformation in energy, and the transformation in energy is caused by work being done. So what we get is finally our result is that GPE is equal to m times g times h. So that's the result, the equation for GPE. So here, just as a reminder to have it in your notes, m is mass in kilograms, g is the acceleration due to gravity, so 9.8 meters per second squared, and h is the height in meters, always in meters. If you have these three values in these units, kilograms, meters, and meters per second squared, you're going to get your energy, the GPE, in joules. So the unit is joules, or J. Yeah, so we could do an example. So the example is going to be, if you have an object with a mass of 8 kilograms, and it's at a height of 2 meters, what is its GPE? How much gravitational potential energy does it have? So in your calculator, you put m, which is 8, times g, which is 9.8, times 2, which is the height, and you're going to get 156.8. So the GPE is the mass of 8 times the g of 9.8 times the height of 2, which gave me 156.8 joules. That's the example of GPE. So that's it. That's the simplest equation, gravitational potential energy. Okay, the following one is elastic potential energy. So let me divide here. Elastic potential energy. Potential energy, or as we're going to call it, EPE. Energy, which is EPE. So elastics are always talking about something that you deform with a force. It requires a force to deform it, to compress or to elongate the original length. And when you let go, it's going to go back to its original length. So the example that we always put here is a spring. So you have, I don't know, suppose this is a wall, and you tie to it a spring. And tied to the spring is a box or whatever, right? So that is the original length. So when nothing is touching it, when nothing is doing a force on it, the box is going to be here in this position that we're going to call x equals 0 meters, because that's where it is when there are no forces acting on it. But you can either apply a force to elongate the spring, which will move the box maybe, I don't know, out here, or you can use your force to compress the spring, and that will make the box be back here. Right, so that's going to be a different x. Suppose that you elongated it all of this distance. This is going to be your new x. Maybe this is, I don't know, 2 meters. Or maybe you compressed it by x equals -1 meter. Yeah, so how much you move it is what we call the compression or the elongation of the spring. That's going to be in the equation. And the other thing that is in the equation that we saw when we saw Hooke's law of spring force last year, at the end of last year, was the spring constant. So there is a constant of this spring that we call K, that determines how hard, how stiff it is, how hard it is to compress or to elongate that spring. So we have basically two values here. We have K, which is called the spring constant or the spring stiffness constant. Stiffness constant, because it says how stiff the spring is to elongate or to compress, and our X, which is the elongation or compression. So usually it's positive if we elongate it, and it's negative if we compress it. So we call it the elongation, because that's the one that's going to be positive. So compressing is the opposite or the negative of elongation. So how much you move it from that x equals 0 position, which is where it would normally be. The Hooke's law equation, we saw it last year, and it depended linearly on the elongation. The equation was F equals -kx. We're not going to use that one right now, but it is similar to the equation for elastic potential energy. So let me write it in the same color. Our equation is actually EPE equals 1/2 times the K, the spring constant, times x squared. So you need to remember the 1/2 and remember the squared every time you do a calculation for elastic potential energy. So that would be the resultant equation. So we can try an example, just like before. So I have a spring. So we have a spring of spring constant K equals 5. And the unit of the constant is newtons per meter. and you stretch or elongate the spring by 2 centimeters. What is the elastic potential energy? So the first thing is we need to remember that the units are always the same, the SI units that we've been using always. So our elongation has to be in meters, and our spring constant has to be in newtons per meter. Okay, that's the only way that we're going to get the right unit for the energy in joules. So what we need to do is put it in the equation, but just remember that these 2 centimeters, we have to convert them to meters. So EPE would be 1/2 times RK, which is 5, times the x squared, which is 0.02, because we moved it twice from centimeters to meters, squared. So it's always going to be a pretty small number, because usually you don't have springs that you can elongate a whole meter or a kilometer. No, you usually just elongate a spring a small amount in centimeters. So we put that into the calculator. So we're going to get 1/2 times 5 times 0.02 squared gives me 0.001. Oops. 0.001 joules. That would be the answer for the example. I'm going to erase and do the last equation. So the third and final energy that we're going to look at today is kinetic energy. So we put it here, kinetic energy, or as we call it, KE. Okay, this one doesn't really have an explanation of where the equation comes from, so I'm just going to go ahead and give you the equation, and you're going to see that it looks very similar to that one. So the equation for kinetic energy is 1/2 times the mass m times the speed squared. This is the equation. So notice that it also has the 1/2, just like elastic potential energy. It also has a constant, and it also has something squared. In this case, it's a distance. In this case, it's a speed or velocity. So this is what we have, and we need to put our mass in kilograms. So this again is mass in kilograms, just like for gravitational potential energy. 1/2, and the V is the speed in meters per second. Always in meters per second. If we use these 2 units, we're going to get kinetic energy in joules. Oops, joules. Right? So we can try an example. It's going to be basically very similar to the previous example. So we have a ball of mass 3 kilograms. Ball of mass 3 kilograms. And it's moving at, let's say, 6 meters per second. What is its kinetic energy? How much kinetic energy or how much energy of motion does it have? So we just do the same thing. We plug it into the equation. So we've got kinetic energy equals 1/2 times the mass, which is 3, times the speed squared. So that's 6 squared. Don't forget the squared. Okay, so we put it in our calculators. 1/2 times 3 times 6 squared, and that gives me 54. 54 joules. So that's it. That's the way of determining the energy that something has thanks to its motion. So basically what you have to remember is in gravitational potential energy, it has more the higher up it is and the more massive it is. In elastic potential energy, it has more energy the stiffer the spring is, so the harder it is to stretch or to contract. And the more you elongate it, the more you stretch it, the more energy is stored inside that spring. And for kinetic energy, the more massive the thing that's moving is, and the faster it's moving, the more energy it's going to have. So that's what you have to remember about GPE, EPE, and KE.